These are the recorded lectures for Chapter 1 on PowerPoint slides, and this is Section 1.3. There is a fourth section on science versus technology, and I will mention that. But mainly for this second week of class, we're covering the scientific method. So the scientific method is defined as a series of steps used in gaining new knowledge through research. So the scientific method helps us to gain knowledge by carrying out controlled experiments. There are 5 main steps of the scientific method, and they are starting with observation, then formulating a hypothesis, designing an experiment, conducting the experiment, making predictions on the outcome of the experiment, collecting data with statistical analysis. We don't focus as much on that in general biology, but that is definitely using statistical analysis to determine if the data collected is statistically significant, that kind of thing. And then a conclusion based on the results of your experiment. So these are the 5 steps, 5 basic steps. If you look at the flow diagram, you're going to start your experiment with an observation or observations that lead you to formulating hypotheses. Your hypothesis is going to lead you to designing an experiment and making a prediction of what's going to happen in that experiment. If the results of your experiment cause you to reject hypothesis 1, you're going to go on and try hypothesis 2, design an experiment to test hypothesis 2, formulate a prediction. And then if your results cause you to reject your second hypothesis, we're going to design an experiment to test hypothesis 3. And so if your results of your experiments confirm your predictions, then you would say that my results support the hypothesis. That will be your conclusion. Looking here, experiment 4 results are causing you to modify your hypothesis and modify your predictions. And then again, you're going to use the results of your experiment to determine in your conclusion if you support your hypothesis, or if your hypothesis is supported or rejected not supported based on the results. So the definition of a hypothesis is a tentative explanation for what we observed. An example is the discovery of the antibiotic penicillin. The hypothesis is developed through inductive reasoning. There's 2 types of reasoning, inductive reasoning and deductive. When you develop a hypothesis, you're using inductive reasoning. The hypothesis is always a statement, and it's always testable. When you design your experiment, you use deductive reasoning to make a prediction, which is the expected outcome of the experiment. So the experiment is a series of procedures designed to test your hypothesis. You always want to make sure your experiment is controlled. In the experiment, you have the independent variable, which is the variable that you are testing. And then you're going to have at least one test group, which is exposed to that independent or experimental variable. Then a control group that goes through all aspects of the experiment, but is not exposed to the independent or experimental variable. If you get the same results for your control and test groups, then your hypothesis is not supported. The data is defined as the results of the experiment. The results should be observable and they should be objective, not biased. You use tables and graphs to present your data. Like, for example, here we have a graph of cholesterol levels, blood cholesterol levels over 4 weeks. It's showing the variation from somewhere around between 175 and 200, and then between 200 and 225. So this would be like 187, 188. And this would be like 212 or 213. This is 200 for week 3, and then week 4 is 175. So our independent variable, that factor that we're testing, is, I'm assuming it's time. Because what we're measuring is blood cholesterol levels, so that's our dependent variable. So our independent variable, what does it really say here? I guess it's just differences in time. I don't know if the diet is being changed or what, but the dependent variable is definitely what you measure, which is our cholesterol levels. So for conclusions and peer review, the data are interpreted to determine whether the hypothesis is supported or not. If the prediction does occur, then the hypothesis is supported. If the prediction doesn't occur, then the hypothesis is not supported, or we can say it's rejected. Findings, especially if these experiments are done at the college or university level under a professor, the findings are reported in scientific journals, and then peers, which would be other scientists, review the findings. And then other scientists attempt to duplicate the findings or to have them dismissed because of, proving them, rejecting the hypothesis when they do the experiments. Now, these are two scientific publications or journals. You do need to know the definition of a scientific theory, because I know a lot of people think a scientific theory is not, does not have as much support. But scientific, we base our textbooks and our research and products that are made, and technology is based on scientific theories. So we do have enough evidence to believe scientific theories are true. Scientific theories are defined as concepts that join together two or more well-supported and related hypotheses. A theory is supported by a broad range of observations, experiments, and data. So it's not as strong as a scientific law, but it is considered a fact when we are teaching science and when we are doing research and developing technology. So a scientific principle or law is a widely accepted set of theories, and the scientific principle or law has no serious challenges to validity, although there are very few challenges to scientific theories. Some examples of scientific theories, so you can understand how strongly supported they are, is, for example, the cell theory says that all organisms are composed of cells, and new cells come only from pre-existing cells. This is something that has not been, we have not found any evidence to reject this theory in many, many, many years. So the only living things, the only organisms that we've studied in biology have been composed of at least one cell. The theory of homeostasis says the internal environment of an organism stays relatively constant within a range that is protective of life. And this is a theory that we have not found any evidence to reject. This is a theory that we base our, we consider this as fact. Now, evolution is more controversial, but the data and the evidence that has been collected is supportive of the theory of evolution. A lot of the controversy comes from the people who don't understand what the theory of evolution is saying. They think it says more or something different from what it actually does. And also, the controversy is based on the theory of evolution. The biggest, I think, controversy is when you get people who believe that the Earth is younger than what it is, and that living things were not around as long as the theory of evolution says that they have been. The theory of evolution is based on evidence that living things have been in existence for, billions of years. So evolution says all living organisms have a common ancestor, but each is adapted to a particular way of life. All living organisms have a common ancestor, but each is adapted to a particular way of life. And what's not here, that I always say, the definition of evolution is change in species traits over time. So anyway, it's not worded that way, but the theory of evolution is not as controversial as what a lot of people think it is, and there is much evidence to support it. So it's just basically, the theory of evolution basically says change over time happens, An example of a controlled study. So what we're going to look at here is that this group, and these are questions too that you'll see in your practice test questions, Chapter 1 practice test questions, and your Chapter 1 homework. There are questions about this particular experiment where they had 3 groups of people, and each group was either given a placebo, they were given an antibiotic A, that was test group 1, or they were given antibiotic B, that was test group 2. And they were examined for the presence of ulcers. And then you can look, it says, I can't see this very well. Let me see if I look at it this way. Okay, well, hopefully there'll be a data table. Well, you can't see it. You can't see the data table. All right, I'm sorry about that, but I guess I'll just tell you about it. So we're looking at an experiment to determine the effectiveness of 2 different antibiotics. The hypothesis says that a newly discovered antibiotic B is a better treatment for ulcers than antibiotic A, which is in current use. A lot of people don't realize that we use antibiotics to treat stomach ulcers because stomach ulcers are typically caused by a bacterial infection of Helicobacter pylori. Helicobacter pylori. I'm not going to try to write that, but Helicobacter pylori is the name of the, I can type it. How about that? Let's go back to, insert text box. Helicobacter pylori. And this is a scientific name for the bacterium that causes stomach ulcers, that can cause most stomach ulcers anyway. You always have to put it in italics, but it's Helicobacter pylori, or H. pylori. And the experimental design says 1 control group includes subjects with ulcers who are not treated with either antibiotic. They're given a placebo. And there are 2 test groups that are either given antibiotic A or B. Now, an endoscopy is a procedure that allows doctors to examine the linings of the throat, stomach, and upper small intestine to check for ulcers. And it's performed on all subjects. The investigators then use statistics to determine the effectiveness of the treatments, and on the basis of the data, the investigators conclude that their hypothesis has been supported. Their hypothesis is that antibiotic B is a better treatment than antibiotic A. So what is the experimental or independent variable in the experiment? And that is going to be the type of antibiotic, so either placebo, antibiotic A, or antibiotic B. And then what is the dependent variable? And that is the measurement of the presence of ulcers. All right, so that's an example of a controlled experiment. And I think the only thing that we didn't talk about is everything else besides the treatment has to be the same. So the test subjects have to be chosen randomly. They have to have ulcers. They have to all have ulcers. You can't just pick test subjects who don't have ulcers. So they're all going to get an endoscopy prior to the experiment to show that they have ulcers. And then they will get another endoscopy afterward, after the antibiotics and after the antibiotic or placebo treatment, that will determine if their ulcers improved. So there's a measurement of whether the ulcers improved, stayed the same, or got better. And that's what the graph shows. Now, last thing is make sure you know the difference between science and technology. Technology is the application of scientific knowledge. Examples are cell phones, new drugs, and then there's a section on climate change, which I really don't ask a lot of questions about, so I'm going to skip it, and a section on emerging diseases, which we will cover in Bio 112.